This mini French session. The first French speaker is Hugo Duminil-Copin. We speak about near critical window in percolation ZT.
Thank you very much. So I'm sorry, I realized afterwards that I didn't know how to read. So there is no random walk in my talk, and even less, I didn't even choose the right dimension because I'm mostly going to talk about dimension 3 and more. But I should say that, there will be many French people without jobs if you would not have contributed with loop arrays, random walk, and everything that followed. So I would like to thank you for that. And also I would like to say, I was told by TBA that I should tell you hi, and that he's sorry because, well, he's still recovering from his poor ski abilities. So, okay, so let me present a little bit what I want to do. So it's a recent paper. It's a small thing, but we are aiming far. Probably we will not get where we want, but at least along the way there are nice things. So I want to discuss Bernoulli percolation on ZD. So I remind you that my percolation is on edges of ZD. Every edge is open with probability P and closed with probability 1 minus P. I will denote the percolation measured by PP. And my goal is to study the phase transition of this model. So I know that there is a critical parameter, PC, which depends on the dimension, below which I don't have an infinite cluster, and above which I do have an infinite cluster. So here there is an infinite connected component, almost surely, and here no. And what I want to study is basically how fast you go from one phase to the other one. So there is a way in physics to measure this by introducing the following quantity. When you are below the critical parameter, in fact what happens is that the probability to be connected to the boundary of the box of size n decays to 0, but it decays in fact exponentially fast. And if you can introduce, it's called the correlation length, which is the speed or the inverse speed of decay of this quantity. So I look at minus 1 over n, the log of the probability that 0 is connected to the boundary of the box of size n. So this thing is decaying exponentially fast, so this is a strictly positive thing, and I take to the power minus 1. So this quantity is basically decaying like exponential of minus n divided by this correlation length. For p larger than pc, of course this quantity doesn't decay at all, but what is decaying is almost the same thing, except that here I put 0 connected to the boundary of the box, but not connected to infinity. So I'm forcing 0 to be in a finite cluster. And then in this case, it decays exponentially fast. So this is the definition of the correlation length. My goal is to study this quantity because, in fact, you have different theorems, which I'm not going to describe here, which basically tell you that if I am away from PC, so take P not equal to PC, and let's look at a box of size n. If P is very, very close to PC and n is not too large, then what you are going to see in this box is basically what you would see exactly at PC. Right? Take, for instance, P, which is like PC minus 1 over n to the d, then actually the two configurations are completely absolutely continuous with respect to each other. Well, psi p is the length at which it starts to differ. If I look at a box of size psi p times psi p times psi p, oh, that was hard, sorry, then you basically see something critical. If you go much above this quantity, then you start to see something which is either subcritical or supercritical, depending on the side on which you are from PC. So this interpretation is, if you can get a bound on psi p, for instance, an upper bound on psi p, then you get a lower bound on the size of the, an upper bound on the size of the window. Lower bound, sorry. Okay. So I should start by saying that it's not at all clear that this quantity exists, right? So the fact that psi p, if I just assume that it is between 0 and infinity, I allow it to be infinity, the fact that this thing exists is already non-trivial. It follows from submultiplicativity arguments. So I'm not going to discuss it here, but already here there are very cute arguments to prove just that it exists. And the fact that it's finite is even tougher to prove, and it follows from two different results. For p smaller than pc, it is a result that goes back to the 80s by Menshikov and independently by Eisenman and Barsky, which exactly prove that this quantity decays exponentially fast for percolation. And for p larger than pc, in fact, the fastest way to prove it, I will go back to this a little bit later, is a result by Grimet and Marstrand, which I think is early 90s. So these are pretty old theorems, but they were really non-trivial theorems. It's not direct that this psi p is finite. It is not very difficult actually to prove that it goes to infinity when p tends to pc. Okay. So the theorem I want to maybe first what is a conjecture? Like that I first showed to you that what you should get, and then you will have you will not be impressed by the theorem like that. If I do the other way, we never know. So conjecture is that psi p is in fact behaving like a power. So it's blowing up like p minus pc to the minus nu plus little o of 1. The little o is in p minus pc, where nu, when nu depends on the dimension. In dimension 2, it's a 4/3. In dimension 3, 4, and 5, it is actually a numerical number that we don't have an actual prediction for what it is, so it's numerical. And above 6, we expect that it's 1/2. So this is a very nice conjecture, and I should say that, in fact, for d equal 2, it is proved, at least in a special case of the triangular lattice with side percolation. So this is proved. So proved by the big team. So there will be Wendelin, Greg, Oded, and Stas, and we could also add Kesten in this. For d larger or equal to 6, well, it's not proved, but at least we know what is happening. So this would be conformal invariance idea. Here it would be the fact that the model has a mean field behavior. And in fact, if D is large enough, you can prove via Lace expansion, so this will be Slade and Hara, that you get 1/2 at least for p smaller than pc. For p larger than pc, so this, there are kind of two theorems. Yeah. What do you do when p is smaller, and what do you do when p is larger? So when p is smaller, Lace expansion really gives you that. Lace expansion is not a technique which is very suitable for the supercritical phase. So there are difficulties for the supercritical phase, but adding a few ideas from the work I'm going to talk about, you can actually prove the 1/2 in the other direction. But it is based really on this mean field results, and also I would say so the original result of Hara and Slade, but also results by Kozma and Narkmias. So you need delicate arguments on the critical phase. Okay, so what would be a good goal if you want to prove something would be to prove that you have a power bound, that there exists a C such that this thing is smaller than P minus PC to the minus C. We are very far from that. Our theorem, and what I'm going to describe a little bit today, so is the following, that there exists a C, so it starts well. The unfortunate thing is the next thing, is that psi p is smaller, and don't laugh, please, because I'm going to explain that smaller than exponential of C times P minus PC, and I mean, if, like exponential is not worse, it's squared here. I mean, minus squared, otherwise would be good. So this is our results. It took us 4 years to get it, and every year we were removing an exponential. So that's, you know, we are getting closer. Maybe in a year we are able to remove this exponential. So, I mean, no kidding, at the very beginning.
We had another exponential?
We had actually a tower of exponential to start with. Then we managed to get to 3, and we were very happy about it. And now we have only 1, so that's not so bad. I'm going to explain a little bit why we are trying to do that, because in fact, removing each one of these exponential required to get a new idea on what is happening at criticality for percolation. And the goal of this project is actually to have like a tractable project on which we can prove things, but the underlying goal is to try to prove that at PC you don't have an infinite cluster, which is a big conjecture. And we are gathering information via this project. So I'm going to maybe try to give you a little bit more information on this connection. Like that you can understand a little bit more why we try to do that. So, yes?
That's the question. If you have a lower bound diverging to infinity,
yeah.
Would this prove that there's no infinite cluster at criticality?
A lower bound diverging? No. The lower bound you have, because you cannot be too small. I mean, psi p, otherwise, you know, C is a dual thing. If you fix a size n, you cannot take, if p is too close to pc, so for instance, if it's pc minus 1 over n to the d, then really just the probability of every configuration is comparable. So you have an absolutely continuous random configuration. So the lower bound, what I'm saying is that psi d is obviously larger or equal to 1 over, p minus pc to the minus d. This is clear. In fact, even you can prove p minus pc to the minus d over 2 is not very difficult. So it will not prove that. And so that's a good question, whether what we are doing could lead at some point to a proof that there is no infinite cluster, and I'm going to basically answer no, but with flowers around. I'm not going to. Okay, so the motivation is, well, to prove this thing, that at PC, probability to be connected to infinity is 0. This is really the big question, one big question. And let me give you, it's not even a strategy, it's just one way of attacking the problem, and then you can interpret it as you wish. So imagine I give you a delta and a sequence En of events. They are events. I'm reinventing the wheel. Don't think that I'm doing something deep. I'm just so a sequence of events depending. So each event depends on the box lambda n only. Okay, so En depends on the edges in lambda n and nothing else, such that two things. The first property, I'm going to call it P1, would be that if I find one n such that this thing is larger than 1 minus delta, so if the probability of one of these events is very close to 1, then I do have percolation, and even because I want to simplify myself, well, let's put, okay, I have percolation. So somehow En is a witness, it's a finite size criterion for percolation. If the probability of this thing is big enough, then I know already, I don't need to look at larger scales, I know already that I will have an infinite cluster. Notice that I didn't put PC here, okay? I said if for some P and some N I have that, then I do have percolation. So this, okay, this is a property. Imagine I have a second property, and this is, which is complementary, which is that if I have percolation, then there exists an N such that I have this property. So basically I'm saying the two things are equivalent. I'm isolating them because I'm going to discuss them independently later on. But there is equivalence between this and the fact that there exists an N such that I have that. If I find a sequence like that of events En, I'm going to give you examples. And if I find the delta, then I automatically find that, in fact, the set of P's for which the probability that 0 is connected to infinity is positive, well, this thing has to be open. It has to be open because it's just the union over n of this thing. And here, now En depends only on finitely many edges, so this function is continuous. So the set of P for which you have that is open. So this will say that this thing, if P1 plus P2, then this thing is open. So if it's open, it cannot contain PC. Okay? That's a very simple observation. Well, you know, it is how you prove in 2D on an arbitrary lattice with sufficiently many symmetries, you do not have an infinite cluster at PC. It's actually a proof like that. You find, you construct events En, which are going to be crossing events, and that's what you use in dimension 2. In fact, even if you look at more general models, like random cluster models, or percolation model with dependency, once again, it is exactly this type of argument that you use to prove that you do not have an infinite cluster. So this is a very general strategy. I didn't tell you anything because I didn't tell you what En is, but I want to illustrate a little bit where are the difficulties. I mean, why it's just a strategy and not even close to be a proof. Well, the catch is that the easier the P1, the harder the P2, and vice versa. The more you put in the event En, the easier it will be to prove P1, because you will have more information here. But the harder it will be to prove this thing. So let me give you a few examples. So example 1. If I give you, for instance, that the event En is the following. So you take a box of size n, take a box of size n over 4 in the middle, and a box of size n over 2, or let's not even, okay, n over 4. And let's assume that the event En is that there exists a path from the small box to the big box, and that the second biggest cluster in this box is very small. So imagine the second biggest cluster, so it's cluster like that, has radius smaller than, say, n over 10. Is it clear for everybody? Don't hesitate to interrupt if I'm... So I'm taking the event that I have a big cluster going from inside to outside, and the second biggest cluster is small in radius. Well then, so this is an event which, in fact, for this sequence of events, P1 is fairly easy to prove. How would you do that? You would just take your graph and just patch it with boxes of size n over 4. Okay? And now you are going to say a box of size n over 4 is good if this event occurs around it. And otherwise, I say it's bad. Notice that, so now I have a random configuration of good boxes and bad boxes. Notice that if I have a path of good boxes, so a path of neighboring good boxes, well, if I have, say, good boxes here and here, I need to have a path going from this box to distance n over 4, to distance 3n over 4, a path from here to here, but also notice that these two paths, by definition, will have length larger than n over 10. So they must intersect necessarily. There is no choice about it. So if I have an infinite path of good boxes, then I have an infinite path of open edges. But now let's look at what is the distribution of these good boxes. Yes?
Let's see why they have to intersect.
Okay, so here, so you have a, so let's take, maybe I should, I'm going to draw it here. So imagine I have another box here next to it.
A small one is good.
Sorry?
So when you say something is good, you refer to the central box?
Yeah, the central box is good if around it you have this thing. Was it the problem? That was the problem?
Yeah.
Ah, sorry. No. I thought that was not the problem. It would have been too easy.
But then you have to have.
Okay, look.
Intersect is not a good word, right? Belong to the same cluster.
That would be a better word.
Okay, that's different.
It's entertaining. Good. Okay, does somebody wants to carry on now? Because you seem to be using better words than me. So yes, I really meant intersecting in terms of clusters. Sorry about that. Yes, of course.
Why do the clusters intersect?
This one now I can answer. So the bad thing would be that, so this guy is, there is a second box like that. This guy has a cluster which is going like that and going to the boundary of this thing, okay? But these two clusters, they have, in this box, in the first box, they have radius larger than n over 10. So they must be the same cluster, because the second biggest cluster had size at most n over 10. Yeah, that was the truth. Okay, so each guy is good with probability 1 minus delta. And there is dependency. It's not independent percolation, but it's only finite range dependency. So there is a famous result by Liggett, Schoenman, and Stacy that say that when you put delta large enough, small enough, this type of 4-dependent percolation is dominating a product percolation with parameter as close to 1 as you wish. So by providing delta to be small enough, this process can percolate. Okay? So this P1 is very easy. The P2 is very difficult, in fact. It's very easy to prove. I mean, if you have an infinite cluster, it's very easy by taking n large enough to prove that there is a path going from the small box to the big box. This is very easy. What is difficult is to prove that the second biggest cluster is not too big. In fact, there are, I mean, that's what you predict in the supercritical phase, but there may be many disjoint clusters going from n over 4 to distance n. So the uniqueness somehow of this huge cluster is what is difficult to prove. So P2 is very difficult to prove in this context. So this was example 1. Let's go to example 2. So the difficulty was coming from the fact that uniqueness is difficult. So let's try to go around this and do something where uniqueness is easy. So you could do for En the following thing. Take a tiny box this time of size Un. Tiny, tiny, tiny. This is still size n. if you do it in a tiny way, just the fact that there is this classical result about percolation that there is a unique infinite cluster, in fact. When there is an infinite cluster, it's unique. So you can choose UN, in fact, small enough that you know that there is a unique cluster going, say, to distance n/2. By choosing UN small enough. Imagine I could do the following. I put another box UN, so let's say this was centered on n/2, 0, and here maybe let's put n/4, n/10, no, yeah, n/10. Do the same here over n/2, 0, and assume that you also have a unique here. So when I say unique, I mean at most one. And let's assume that I can prove that also I take the event where I also have a path from this small box to this box. Now notice that I can once again do some kind of coarse graining. I take boxes as before, but this time I look at edges and I'm going to say an edge. So they are a distance n of each other. So I do the same thing like that. So I have like edges like that in my renormalized lattice. And I say an edge is good if this event occurs. Notice that if I have now a path of open edges in this renormalized lattice, then a path from here to here, I mean a cluster from here to here, and a cluster, say, from here to here, they must intersect because there is a unique cluster from the small box to the big box. So these two clusters must be the same. So once again, you manage to do a renormalization. So here, as I said, the difficulty is not the uniqueness. This follows basically from the uniqueness of the infinite cluster. Here, the difficulty is that you know that there is a path. I mean, it's also easy to prove that there is a path going from here to the boundary. But why on earth would it go through this small box here? So in this case, the difficulty in proving P2 is to go from this guy to this guy, very precise. So that was example 2. So in these two examples, P2 is difficult to prove, P1 is easy. Okay, let's try to find, I mean, I'm going to give you a trivial example of something where P1 is difficult to prove and P2 is hard to prove. No, the opposite. This I can also give, but so there is one thing which you could just take a very small box, UN, and just look at the event that there is an open path like that. This is trivial to have lower bound on this, so P2 is trivial in this case. P1 is extremely difficult because you don't know how to patch cluster. When you do your coarse graining, you don't know how to patch clusters together. So this is very difficult. But still, I want to emphasize something that, so here P2 is easy. So this was example 3. P2 is easy. P1 is extremely difficult. But P1 of epsilon is easy in the following way. Imagine that I allow myself to actually add an epsilon here. I give you the right to increase a little bit the percolation by just epsilon. Well, I claim that for any epsilon, there is a delta and an n, such that if this event, if the probability of this event is close enough to 1, so if the probability of En is larger than 1 minus delta, then the probability at p plus epsilon of 0 connected to infinity is positive. And in fact, you can even prove something a little bit stronger, which is that you can even prove that it percolates in a slab. In fact, you don't even need the whole ZD. You can only percolate in a thick slab. So this is exactly the content of the of the Grimet-Marstrand theorem. If you allow yourself a little bit of increase, then you percolate. So you see, that's where we stand as for today. Is we have one P2, I mean, there is a case where P2 and P1 epsilon is provable. And what you would like is to get rid of this epsilon. We don't know how to do that. But our idea was that, okay, we don't know how to get completely rid of epsilon. Can we make epsilon quantitative, going to 0, and at which speed can we make it go to 0? So obviously, this strategy will never really give you 0. So that's why it's not a direct strategy to prove theta PC equals 0. But along the way, what you have to understand is what is going on at criticality, how you renormalize things, and so on. So we are hoping, and actually up to now that's what is happening, that to improve this epsilon, to make it more and more quantitative, you need to understand more and more what is going on at the critical level. So that was our motivation for this class of problems. It's not so easy to find problems which are tractable on Z3, say, on critical percolation on Z3, that you can try to attack a little bit, because, I mean, if nobody attacks this thing, we will never get there. So Raphael Cerf is very good at finding good problems, and we are trying to follow his lead, but well, so that's the best we came up with. Sorry. Okay. So let me try to give you a little bit more juice on this thing. So the first part of, I mean, there are kind of two arguments somehow in our paper, two parts. One is going to be a kind of quantitative Grimet-Marchand theorem, saying if you have that the probability of En is larger than 1 minus delta, what is the best epsilon you can find? It's going to be the first thing. And the second part is going to be a little bit different. The second part is going to be, okay, let's try to prove the first one with the best delta possible. These are two complementary things. So the first part, this quantitative Grimet-Marchand, I'm not going to describe the proof at all. Quantitative Grimet-Marchand. I'm just going to state the theorem. But there is already there some interesting features. So there exists a constant alpha, and there exists a C such that if the probability of the box of size n to the alpha to be connected to the boundary of the box of size n is larger than 1 minus exponential 1 minus epsilon, then in fact you percolate, and the increment, well, maybe I should put delta here because that was a delta later before, log 1 over delta, you percolate in the slab of width n. So what I'm claiming in this thing is that the epsilon you can take C over log of 1 over delta. That's the content of this theorem. And just here notice that I'm fixing un to be a power of n. I'm going to tell you exactly, in a second. So the bigger the alpha, so the closer to 1 this, then, the easier it would be to prove a good bound on the probability of the event En, right? So what I'm claiming is that, well, I cannot do it for any alpha. There is some minimal size of alpha for which I can do it. Below this size I can, above I can't. So let me tell you what is this alpha. At least like that you will have one thing out on this theorem. Why can't I take alpha so close to 1? Well, because we are using, I kind of already spoke a little bit about that. One of the main difficulties in understanding critical percolation in Z3 or on ZD is the fact that these clusters, there may be many different clusters which do not intersect. Many different paths that miss each other because you are in a big space. You have room. It's not like in Z2. By the way, there is an actually quantitative way of talking about that, just this is a parenthesis for expert people. It's called the hyperscaling relation. That hypothesis that basically in dimension 2, 3, 4, and 5, you expect that in fact clusters do not miss each other. You don't know how to prove it in 3, 4, and 5, but that's what you expect. In dimension 6 and more, they start to really miss each other. So there is really even kind of physical predictions on the dimension at which things really start to be bad. But you don't know that it doesn't start to be bad at dimension 3. So you're already stuck in dimension 3. So we need somehow this kind of uniqueness zone here. The fact that if there is a cluster going from inside to outside, it's unique. There is no two clusters like that. And there is a beautiful result, recent result of Raphael Cerf, which I guess went a little bit unnoticed, but it's actually super useful for any type of percolation problem in dimension 3 and more, which is the following. He proved that there exists an alpha. In fact, he has an explicit bound, but this is not so relevant. There exists an alpha such that sorry, the probability of a path from n to the alpha to n, the probability of two disjoint paths, this probability is decaying like 1 over n to the alpha. So the alpha that we are using here is exactly the alpha which is allowing us to have this uniqueness zone here. That if there is a cluster crossing, it's a unique one. There cannot be two such clusters. So this is the reason for the n to the alpha, and we are going to take this alpha now, which is, I think, in dimension 3, 1 over 17 or something like that. And notice that if you could improve this alpha more and more, and for instance, if you could put, instead of n to the alpha, if you could put, say, n over 4, then you would have proved the property P2 for this guy, basically, or something like that. So it's exactly, that was another way that Raphael was trying to attack the problem of theta PC equals 0 was to say, okay, I want this uniqueness, this is really what is important. Let's just allow myself more latitude and then try to improve this thing, try to make it bigger and bigger. So that's another way of going there. So that's the reason for this alpha. So I'm not going to describe really the content of this theorem. I'm going to rather tell you a little bit more how you get a good delta there. Okay, so there are going to be a few steps. So what we want to prove so if I want to prove this bound, I need what? If I want this, another way of proving that is saying if I take a box, if I take P0 of n, such that I have psi of P0 of n smaller or equal to n. So I take a P for which I know that the correlation length is, larger or equal to n. Then, if I want to prove this result, what I basically need to prove is that at P0 of n plus constant over square root log n, I am way above the critical point. So for instance, what I could try to prove is that at this value, I even percolate, so let's call it P3 of n. At P3 of n, I could, for instance, try to prove that I percolate on z2 times minus n to the d minus 2. If I can prove that, then I prove this theorem. It's just a dual way of looking. Either you look at p and psi p, or you look at psi p equal n, and you look at which p has this value. So my goal is to start from a value of p for which I know that the correlation length is at least n, and try to increase p and try to get more and more information on my percolation to be able to prove that at this type of value, I'm going to have percolation. So now, because of this result, I see that what I need to prove is in fact find, say, a P2 of n of the form P0 of n plus, so this was C3, say, C2 over square root log n, for which I have this property but with probability 1 minus exponential of minus square root log n. Right? If I do that, I see that the log of 1 over delta is going to be square root log n, and I get exactly this quantitative Grimet-Marstrand will allow me to go from this P2 to this P3. Okay? I lost everybody. Everybody's like, oh my God, what is happening to me? Where did I lose you? Who was lost before P3? No, I guess I will not get anything from this. Okay. So P3 was just a dual way of looking at the theorem. And here P2 is just, if I can prove that, then I plug it here, I plug it with delta equals this thing, and I get that at P2 plus C over square root log n, I have percolation. Okay, so at P3, which is going to be here, you could put C2 plus C, you get the result. Yes.
Did you erase the theorem that you are giving?
Yes, I did erase the theorem.
It's equivalent to...
Yeah, but it's exactly equivalent to this statement, that if you start at a P0 for which the correlation length is larger or equal to n, then if you increase by C over square root log n, then in fact you are already way above. You only need to prove that you are above PC. And I'm going to prove that by proving that there is an infinite cluster. In fact, in something even smaller. But the thing is that if you do it like that and you prove that you have percolation in this thing, in fact, you prove even more. You go on the other side. It allows you also to prove that you have the psi p for p larger than pc. That's why I'm going to prove that. But let's not just think. Okay, just think of just proving percolation. Let's not. It will give at least one bound, and that's already sufficiently good for this talk. Okay, so I need to find. My point is I need to find a lower bound of the order 1 minus exponential of minus square root log n. That's what I'm aiming for. So let's start. So step 1 is I'm starting from P0 of n. So the P0 of n is just a P such that the probability that 0 is connected to the boundary of the box of size k is smaller than e to the minus k divided by n. Right? This is exactly an equivalent way of phrasing the fact that the correlation length is at least n. Okay, sorry. So what does it tell me on the configuration? What does it tell me on P? Well, it's not completely obvious. But there is one thing, for instance, that you can look at is maybe let's look at the expected number of points on the boundary of the box of size n connected to 0. So let's look at the sum over x on the boundary of the probability that 0 is connected to x at this P0n. Any guess on a lower bound on this thing? Well, imagine this thing is smaller than, say, 1/2. And think of, if I need to go from 0 to distance k, then every n step I need to intersect the box of size n around me. So I'm going to be able to decompose any path going from 0 to distance k into a path I'm going from 0 to a point x1, which is at distance n of myself, then to a point x2, which is at distance n of x1, etc., etc., etc. So I can decompose my path like that, and just using the union bound and the BK inequality, if this thing is smaller than 1/2, then because I need to do at least k over n steps, then the probability of connecting from 0 to distance k is going to be in fact smaller than 1/2 to the k over n. So 1 over e would be preferable probably. Okay, so this is a little bit fast because I don't have infinite time, but let's say that if this expectation is too small, then I can really think of a subcritical Galton-Watson tree. Okay, you are trying to go, you see your cluster as something branching, but it branches with probability, with a mean number of guys which is too small, so the probability of getting far is going to decay exponentially fast, and you can actually estimate that. So what you get from that is that if this is true, then in fact the probability of connecting to distance k is going to decay faster than e to the minus k over n. So this is not possible. This is larger or equal to. Okay? In fact, here I use a set lambda n, but I could have used any set S included in lambda n. If I give you a set S included in lambda n, you can do exactly the same thing. You start from 0, you look at the first time you exit this set S, and then you start from this guy, you look at the first time you exit this set S around this guy, and so on. So this is saying that, here, that anyway, whatever the set S included in the box of size n, the expected number of points on the boundary of the box, which is connected to 0, has to be larger than 1 over e. Otherwise, I have a problem. So now, in a recent paper with Vincent Tassion, we prove the following thing. We prove that if you have things like that, so let's call this thing phi p of s, it's a quantity, then you have a differential inequality, which is the following. The derivative of the probability that 0 is connected to the boundary of the box of size n, this is larger or equal to 1 minus this probability. And here there is a factor in front, which is the infimum of the phi p of s for s included in lambda n. So in particular, you see that as soon as you know that all these phi p of s are larger or equal to e, well, the probability of e connected to the boundary of the box of size n has to grow, to blow up, to grow linearly at least. So if I started from p0,
This infimum is smaller than the original probability of reaching the boundary.
no, because it's the expected number. It's the expected number of points. Yeah, so that's the subtlety there. And so this differential inequality allows you to do something that you didn't know how to do before, which is that if I look at p1 of n, which is p0 of n plus 1 over square root log n, then at p1 of n, the probability that 0 is connected to the boundary of the box of size n is larger than 1 over square root log n. And maybe there is a 2e here if you want to be careful, but it's of order 1 over square root log n. So we are still very far from this type of estimate. We don't have something positive. We are not starting from the box of size n, but at least we have a bound which is 1 over square root is small, right? Square root of log. Notice that if you look only at p0 of n, the best bound you could get on the probability of 0 connected to the boundary of the box of size n would be, well, the sum is larger than 1 over e for all the points on the boundary. So 1 of this x has a probability which is larger than 1 over the size of the boundary. So 1 over n to the d minus 1. So the best bound you can give a priori on the probability that 0 is connected to the box of size n is 1 over n to the d minus 1 at p0 of n. But at p1 of n, you have a much better bound. It's 1 over square root log. This is step 1. Step 2, so notice if you have that, of course, you have also that. That's not. Now what are we going to do? We would like to prove we are far from the truth because we want something very close to 1. And we are now just a little bit far from 0. That's all what we get. So what we're going to use now is a sharp threshold theorem. So what is a sharp threshold theorem? So there is this result going back in the original result was by Calais and Lineal, and then it was improved in particular by Bourguin, Kahn and Calais, maybe. I'm always a little bit confused, all the 4 guys. Anyway, it works for every p now, which is the following theorem that there exists a constant, for every epsilon, there exists a constant that depends on epsilon only, such that if you take any p in epsilon 1 minus epsilon, any n, and any box, any event, A, increasing. So an event which is increasing is an event for which when you open an edge, you remain in the event. But if you never saw that, just think this event, okay? Let's call this event A. For any of these things, the derivative of the probability of A is in fact larger or equal to this constant C times the probability of A 1 minus the probability of A. So this is the variance of the indicator of the event A. And you get an additional log of 1 over the max, what we call the max influence, so the maximum of the probability that E is pivotal for the event A. And this is for every edge E in lambda n. So if you never saw what this E pivotal means, I'm not going to explain it to you because you don't have, sorry, this is, yeah. I'm lazy to rewrite it, but but anyway, so you probably already heard of Rousseau's formula, which is telling you that the derivative of the event is in fact equal to the expected number of pivotal points. Here it's something which from this differential inequality you can get something a little bit, different, which is that in fact you have a lower bound on this expected number of pivotals. It's always larger than constant times probability of the event, 1 minus probability of this event, times the log of 1 divided by the maximal influence. Why is it useful? Because usually what we have done, and actually Bella is one of the main players in this thing, is that if you look at an event A, which is invariant under translations, so let's say you go on a torus instead of looking at a box, and look at an event which is invariant under translations, then all the influences are the same. All the probability of being pivotal are the same, because every edge plays a symmetric role. So then, what you get, in fact, there is a small work that you can do about it, and you can prove that in this case, the probability of being pivotal, this quantity is always larger than log n times the probability of A, 1 minus the probability of A. It's an easy corollary of this thing. And it's a beautiful use, because if you have that f prime is larger than f 1 minus f times log n, then you can get lower bounds on the blow-up of f. In particular, in our context, notice that if I could give something like that, you start from a function which is at p1 of n is larger than 1 over square root log n. If you have this bound, then at p1 of n plus 1 over square root log n, this thing is, or maybe constant 1 divided by square root log n, then this thing has to be larger than this thing. I let you integrate out this thing, but that's what you would get. In fact, you have many more applications of this type of inequalities. It has been very fruitful, in particular for dependent percolation models, because it replaces very well the lack of the BK inequality. So this is actually a very, very important contribution to percolation theory that you made. So if this guy is P2 of n, I will be finished. So my point is to try to prove this. I have less than 5 minutes, but I'm almost done. So proving that will be my goal. So what I would need is to try to prove that this quantity, this max influence, is in fact polynomially small. So I could try to adapt to do the original proof and to try to make this event, which is not translational invariant whatsoever, into a translational invariant event. But I'm sure that people who try to do that see that this is not a straightforward thing to do when you have a very small, this is really not a translational invariant event because you really start from a small seed. So this technique to try to make it into a translational invariant event, we didn't manage to do it. So what we had to do is actually to do something which I think may have also use in this type of things, is that, well, let's do a dichotomy. Maybe it's small. Okay. So case 1, in fact, the probability is small. It's smaller than 1 over n to some epsilon, tiny epsilon, for every edge. Then, by definition, my maximum is small, and I have my log n here. I can integrate out, and I'm done. So the case 2 is the one which is more troublesome, and because I have no time, that's practical because I'm not going to have to describe it to you, which is that if there is an edge which is larger than 1, for which the probability of being pivotal is larger than 1 over n to the epsilon, what we are doing is that we are actually proving that there are many edges like that. There are n to the delta such edges, where delta is in fact much larger than epsilon. So here there is really a game of, okay, if an edge is pivotal with large probability, you should be able to prove that in fact, locally you have many other edges with very large probability of being pivotal. And that's what we do. But then if you do that with delta larger than epsilon, then you can go back to the original formula on, the original Rousseau's formula, and says the derivative is larger than the expected number of pivotals, which is larger than n to the delta. So the expected number of pivotals is going to be larger than n to the delta times 1 over n to the epsilon. So if delta, you manage to make it larger than epsilon, you are done. So that's actually here, there is a cute argument dealing with this type of things, and we believe that it may have other applications to other contexts. Just a word, like 1 minute to tell you what is next. So you notice that, if you looked a little bit, there is a barrier. There is a log n that you cannot really beat. If you just do it by hand, this theorem will never give you more than log n. And this log n, if you look at the increments, maybe you can, this square root log n, you can improve it to 1 over log n, but actually, it really looks like 1 over square root log n is a barrier from this point of view. So if you want to use the sharp threshold theorem, you are stuck at 1 over square root log n. So if you don't want to use it, you need really to go into the number of pivotals, or more precisely, if you want something which seems to be more promising, to look really how big this thing is at criticality for percolation. What is the expected number of pivotals? And there you of points on the boundary which are connected to 0 in the surface. And there are very interesting things on the branching nature of the critical cluster for Bernoulli percolation, and this would be the next step of understanding for this critical percolation on these 3 and more. That will be to understand this geometry of the cluster. So really all these things here, it's related to the geometry, but in a more naive way. So every step you gain, you need to understand something a little bit better on the critical percolation. Well, thank you very much.
Thank you for the talk. Are there questions, remarks? Yes.
You mentioned a theorem by Raphael Serf.
Yeah.
What was the, oh yeah, that one is still on the.
Yes, okay.
It was not clear where you used it. Can you say?
Okay, so it's not clear because I didn't show. Actually, I use it in many places. Many, 2 is not so many. In 2 places. In fact, in the proof of the theorem of the Grimet-Marchand theorem, you need to understand, to do the renormalization in an efficient way, this event, this En, is not really what you want to work with. You want to work with an event a little bit different, which is take a self-avoiding path going to the boundary of the box of size n over 2. What is the probability that this path is connected farther away? And to be able to relate this type of probability, so going from a self-avoiding path to boundary of the box to this event, which is, I mean, En was the probability that the box of size n to the alpha is connected to the box of size n. To do that, we use a uniqueness there in a very heavy way. The second place where we use it is in this case too. Here we use it to actually.
Can you say a few words about the proof of?
So it's not a trivial thing, but I mean, in summary is that what you can prove is that the probability for an edge to be pivotal for basically any event is smaller than 1 over n to the d over 2, so square root of the volume. And the reason is that just if you look at the sum of the probability of being pivotal squared, in fact it's smaller than the variance of your function, Poincaré type inequality. So this is the first observation. It's true for Bernoulli percolation. It's true for many more things. So probability, if you want, for n to the alpha equal 1 edge, then it's obvious that it's 1 over square root of the volume. And then if n to the alpha is small enough, you can do some surgery to prove that if you have 2 clusters arriving to the box of size n to the alpha, then you can construct a pivotal with not too small probability. But because the probability of being pivotal is 1 over volume, if this not too small probability is a very small power, for instance, you get that the event that you started with couldn't have big probability. Is it? We can talk about it later. I can really explain more.
Hugo, I'm not absolutely sure that you can't use that still, because it's extremal only in a very rare. I mean, the extremal sets are very small. So if you can prove about KTL some stability, some strong stability result, and I'm sure it will give much stronger.
Yeah. So that would be actually, this is a so I think what you mean, if I can rephrase it to, it's that the guys for which you get actually this log n, the guys for which you have the smallest probability, they are the tribe functions, and they have a fairly, I mean, compelling geometry. Like the geometry of this thing is not at all the geometry of the events you are interested in. So maybe for the events you are interested in, you may be able to prove that they are far from these tribes and that the derivative is much bigger for them. This will be a huge contribution for the following reason, that this log n is usually basically ruling out I mean, if you can get more than log n, then you manage to get away from ranges for which you have polynomial decay of, say, probability of being connected or things like that, which is exactly the range that you want to get away from to prove that you have sharp phase transition, that you have exponential decay in subcritical, that you percolate very well in supercritical. If we go back to, for instance, the talk of Alain Sol, he mentioned all these U star, and so on. These guys, they would all be equal if you would manage, I mean, well, I'm oversimplifying, but it's just an illustration that if you get here much more than log n, or actually not much more, log n times a function which is going to infinity, then you would be able to prove this type of things. So this is actually a very nice way of trying to pin down these things. We tried, and apparently we are not smart enough. Or this thing is too smart. I don't know. One of the two. But we didn't really manage to do that. But this is indeed a natural way of attacking the problem.
Okay. No other questions? Thanks, Hugo.